Hello everyone, I'm Dongliang and I have nothing to disclose. So first of all, Dr. Cheng Liu is from the Nanchang University, China. He's very sorry he cannot be here. So basically, the MRO data are considered as corrupted by the wide additive Gaussian noise in real and imaginary part respectively. Usually what we did on like a simulating MI data, we add Gaussian noise in two parts. But the noise in MR magnitude images can be well modeled by a Rayleigh distribution. And more recently, due to the powerful learning ability, deep CNN has been widely used in image restoration task. And especially some advanced models with increased field size and field number, it has exhibited successful performance in the application of image restoration and super resolution. And in this work, we proposed a Rayleigh net to deal with the Rayleigh noise denoising. Now here is the flow chart of our model. It consists of two parts. So it employs a two Rayleigh net structure, where the first one is the conventional Rayleigh net, and the second one is in the feature space with two convolution layers. And these two layer structure further enhance the nonlinear mapping and deepen the network simultaneously. And specifically, the first Rayleigh net consists of 5 layers, and is used and is for approaching the Gaussian distribution in the spatial domain. And the second subnet is with 3 layers, and it was used to approximating the sparse distribution in the feature domain. Since, as we know, the Rayleigh noise can be approximated by Gaussian noise with very high SNR, and in this work, we assume that the usually normal Gaussian noise can be modeled by a Rayleigh noise can be modeled by a Gaussian noise with another noise whose distribution is irregular, but which we observed it's sparse in the feature domain. That's what we assumed. And in this work, we adopted a progressive network training strategy for fitting the Rayleigh noise distribution. That the first learning strategy is we call it a joint learning. We put the subnet 1, subnet 2, and the training together. But in our work, firstly, we train the subnet 1, and we get a model, which is used as the initial model for the following joint training. So this we call a progressive network learning strategy. And in our work, the batch normalization operator is only used in the first sub-Rayleigh net, while not used in the second one. That's because the batch normalizing has its own advantages and disadvantages. Since it can accelerate network learning and boost accuracy while normalizing the weights and the parameter to avoid other layer in the intermediate feature maps. But simultaneously, it may get rid of the range flexibility from network by normalizing the feature. That's why we use the different strategy for adopting the batch normalization operator. Here is the illustration of the first subnet. Here is the input and the final output, and at the top and the bottom we show the histogram. So we can see for the output, actually it means, or it demonstrates that the noise distribution is more like a Gaussian distribution. So that's our first assumption, that the first subnet try to remove the Gaussian distribution noise. Here is our second subset. Now the input is the Gaussian denoised image, and it with a Rayleigh net, but with a convolution layer. And here is the output with the noise, and we can see this noise is sparse distributed. Here is our experimental setup. It counts the training and testing in total 480 T1 weighted brain images, and with 400 for training and 8 for testing. And the noise brain MI image are generated or simulated by adding 8% Rayleigh noise. And the field number in our Rayleigh block for both subnets is 128, and the field number in the convolutional kernel in our second subnet is 46, and the field size fixed to 7 to 7. and this is our hardware. So here's the experimental results with a quantitative evaluation with PSNR, SSIM, QILV, and MSE for the different denoising method. It's a non-local mean. This is unbiased non-local mean. It's BM3D and a proposed method. In this table, we show the results on 3 images. And we can see for the RationNet, it's almost the best performance for almost the cases. But only for this one, it's very close to the best. And here we show one example for the images with T1 weighted images with a Ration noise level of 5%. From left to right, it's ground truth. It's a noisy image. It's a denoised image by non-local mean. And the bottom line from left line, this is a image denoised by the unbiased non-local mean. And the BM3D and the proposed method. It can clearly see the more structures are preserved after denoising when compared to the other 3 methods. Here is the difference images for different methods. We can see these are different images. We can see many feature loss or detail loss in other methods are alleviated in our proposed methods. We also discuss on the different filter size in our proposed method with 50% Ration noise level and 4 images. And for the left figure, it shows the time with 4 images with different size of filter size, different size of filter. And the right, the PSR for the different size of filter. And we can see as the filter size become larger and the superior performance can be achieved, while at the cost of running time. So that's why in our work, we choose the filter size 7x7 at the convolution area in the RationNet. Here is discussing on the different filter numbers in our proposed method with 5% level of Ration noise. And we also compare the time and the PSNR. We can see that the filter number increased from 64 to 192, and we can get a better and better performance, but also at the cost of running time. So in our work, we choose the 128 filters in the convolution layer in the RationNet. We also try to study the model sensitivity to the learning strategy in this work. So we use the PSNR assessment and the time for the MI data and with a different network structure. Here, for this line is only for the subnet, training subnet 1, and this line is for the subnet 2. Here is for the joint learning, and this is for our progressive learning strategy. We can see the proposed learning strategy achieve the best performance for when compared to the other learning strategies. Here's a conclusion. So in this work, we propose a progressive network learning strategy while fitting the Ration noise distribution at the both pixel level and feature level, use 2 subsets. And our preliminary work proved that it can successfully apply to Ration denoising in MI images. Thanks for your attention.